Well, I think we can start. Welcome back, everyone. And congratulations on getting through the second exam. I forgot to add the actual summary statistics here. I don't like to post a 5 number summary, but I usually like to post the average grade and what the maximum grade was. So I'll get that posted on Friday morning. Also, I'll be posting the exam 2 solutions. So if you'd like to just have an extra thing to take a look at, if I didn't put enough clarifying marks on your exam, that'd be another document that you could take a look into. As far as preparing for the final exam goes, you have several great resources you're compiling already. You have your exam 1, exam 2 review sheet. You'll make a third one for exam 3. I would file those away in a folder. Keep your exam 1, your exam 2. And what I'm going to be doing for all of the exams is I'll always have the solutions posted, but I'm also going to post blank exam 1s, exam 2, exam 3s once we get through all of our exams. So if you want to just rerun exam 1 or exam 2 or exam 3, you will have the solutions available and a blank exam that you could just download or print off if you like. We'll also be just doing the same kind of thing that we did on all the exams, post a mega list of problems for the final exam review, version 1 and version 2. It is a comprehensive exam, but I can't ask every single question this semester. So you'll have a pretty good idea of what's going to be included on the exam based off what did we do on exams 1, 2, and 3. Also put it together all of your quizzes as well, and that'd be another thing to keep in mind. The exam questions, including even the final exam, are meant to be similar in spirit, similar in format to what the quiz questions look like. So keep doing what you're doing. You'll be in great shape coming up for exam 3. We'll post the information what goes on here when we're at the end of this weekend. We'll know what's on it. All the review materials you expect, we're just repeating a pattern at this point. At the moment, we're at a pretty exciting part of the course. This class is kind of divided into two. The first half of the class was all about descriptive statistics, a little bit of modeling. We're looking into things like summary statistics, maybe modeling with a normal distribution or a regression line. But the second half of the course is full-on inferential statistics, which is really the major objective of the whole course. Chapter 10 bridges the gap, so we'll spend some time getting through Chapter 10. Big ideas in Chapter 10 is we're talking about population versus sample again. We're seeing how to collect the data, randomization. We're looking into what conclusions we can make based off if it was an observational study, an experimental design, and then we'll take another careful look at statistic versus parameter. So it's a pretty short section despite all that. I don't have any good questions out of my lab statistics, mainly because when I looked at the selections that they gave us, they just didn't seem really targeted to the spirit of what we're trying to achieve in that chapter. It's also a pretty big chapter, so if you do the reading, you're going to notice we didn't cover everything in there. So if you decide to skim over some of those ideas and focus on the content we covered, that wouldn't be a bad way to read that chapter. So this is going to be the rare one. This is the only time I don't actually have a MyLab assignment that goes along with it. As far as the questions could be from this exam, or excuse me, from this chapter on an exam, they'll be highly similar to these actual problems on the notes, only because I would realize you didn't have the multiple practice of doing this as a MyLab statistic assignment. Well, we briefly talked about what we were going to be doing in this section, like in the last 5 minutes before we called it a night. We're looking once again into a big dichotomy of a population, the entire collection of everyone we want to learn about, versus a sample, a part of the population which we select and decide to study. One thing that's really interesting about doing this kind of thing is the best way to get a nice random sample is through this particular sampling design, the simple random sample. And a lot of this stuff can go wrong in lots of interesting kind of ways as well. So let's imagine just kind of a random scenario. Let's say for a population, it'll be all ISU students. And I don't have actual data of who's registered for fall 2025, but I think spring 2025, it was something along the lines of 11,000 students. So probably about that same amount. So that's our big population. The thing we want to study is going to be mu. Mu is a parameter. We briefly looked into what mu is when we were looking to things along the lines of, say, the normal distribution. We called it the population mean. Let's just redefine it here, just for the sake of having an extra resource. Mu is equal to the population. You can make that possessive. The population's mean is a nice way to say it as well. We usually often say just the population mean, but this gives it some agency. It makes it feel like it's doing something to something else, a population. Mu in this problem is going to be the mean, or you could say average, and it's fine. Mean GPA of all students, namely the ISU students. So this is a quantity that can be calculated. If you work for the registrar office and you have high enough clearance so you can get into all of their databases, that's probably just a little code that you write out and it'll give you average GPA of every student registered at ISU right now. So it's typically an unknown quantity. ISU is not going to share this with everybody necessarily. Sometimes this is something that they're going to keep up their wraps, unless it's really high and they want to advertise. Most of the time, these parameters are unknowns. And you can imagine this is something we want to learn about. It could be an agency in Idaho. It could be a competing university in Utah or Montana. If we want to find out what the mean GPA is of all students at ISU, and we happen to know our average GPA is higher at a different school, that'd be something that we could advertise. It's coveted information. People want to know this. So that would be something that we'd like to study if we are, say, a competing university. We can't contact every single ISU student. So just like on the first day of class, that's the important role of the sample. We'll select a random sample instead. Let's just say first, sample. Imagine how this could go wrong first. Let's do like the worst sample ever, and then talk about why it's a really, really bad sample. Let's say for our sample, this is going to be all, let me count, 6 students in attendance for math 1153, section 11, that's us, at 7:37 p.m. October 2025. So that's now, I forgot the day, October 23, 2025. That's a sample for sure. And if they give us enough incentive, maybe we would be willing to say what our GPA is for the moment. I mean, midterms just happened. So even if you don't have a prior semester, you could give a midterm grade and they could use that in a computation. They probably would have to give you a pretty strong incentive. People don't just say that to a random polling agency. But that's a sample. And you can imagine there's a big problem with this. You could use this sample and you could calculate Y bar from the sample. This is going to be the sample, or the sample's mean GPA. And what do we like to do with that sample mean? We use inferential statistics and relate it back to the population, all ISU students, and we would love to make the claim that the unknown, the population's mean mu, the mean GPA for all students, would be approximately equal to Y bar. But it isn't always true. It just depends. The problem isn't that the sample is necessarily so small. We can still say it's approximately equal. There's just a big error in that estimate. But there's something even worse about the sample. Anyone see what would be just really bad using the sample, relating it back to the population?
One class.
Yeah. Would you say this one class represents the average typical student at ISU? Probably not. I agree. The trouble is, I mean, we're in a satellite campus for the first part, right? There's something exceptional about this. We're also one of the latest night classes at ISU. We're exceptionally late running. I mean, a lot of other things. We're specifically a statistics class. And people who take statistics could be very different from people who are focusing on other things. Plus, we're undergraduates. Plenty of ISU students are graduate students, maybe in a master's program, a PhD program. Some of them aren't even degree seeking, they're just students. We're very specific people, all 6 people here. And so this is not a representative sample for a multitude of reasons. And that's what we want in our simple random sample. Plus, there was no randomization, right? We just took who was here convenient today, and we're asking them kind of a strange question to ask a person, what's your GPA? So we can compute an average. So all these things go wrong, and it gives us something that is the opposite of what we want our random sample to do. A simple random sample is an excellent sampling design, and it gives us something that is representative of the underlying population. But like we mentioned, this is not representative whatsoever. Let's just list off some of the things that we mentioned. This sample is not representative because, let's just list these out. Probably the biggest issue is number one, it was not random. You're not here randomly, you're not 6 random ISU students. There's a particular reason you're all here. You're enrolled in Math 1153, Section 11. So number one, it wasn't random. 2, this is a satellite campus. And sure, ISU has multiple satellite campuses, but of those 11,000 students possibly registered for fall 2025, a lot of them are on the main campus. A lot of them aren't on any campus at all. A lot of them are fully online students. We would hope that our representative sample is maybe larger than 6, but 6 isn't the main problem. We want to have students that are on the main campus, fully online students, maybe not associated to any campus whatsoever. Maybe someone on the Meridian campus way out there on Boise. That's a pretty big campus as well. We took everyone in one particular satellite campus on Idaho Falls. So this is a satellite campus, was a second problem. Third problem, and let me know if I just forget anything or just something jumps out at you. But third problem is all of us are undergraduates, all students are undergraduates, so we just missed everyone who is a different kind of student. And maybe the fourth small problem with this is, again, the sample size is pretty small. 6 is not very great for really capturing a population. If it's the best we can do because the study is expensive, some studies really do have low sample sizes, but maybe it's something to mention as well. The sample size is very low. Notice that's on the bottom of the list. The major thing that's a problem here is we never took a random sample. And because of these issues, it turns out that this is not true. This is not representative. Let me say it as a sentence, not a representative sample. It wouldn't even be a good sample if our population was all ISU students based off the satellite campus at Idaho Falls. That wouldn't be good either because we're a night class and there's plenty of ISU students on this campus who are not night class students whatsoever. So really, if we take the 6 students are available to us and we lost randomization, statistics is already broken there. And everything else is just a further complaint causing this big problem. Mu is not even remotely close to Y bar. There's no guarantee. And if it is close, that was just a coincidence and a remarkable one at that. So we need to do better. What we require is a random sample, first of all. If we can find a way to take our simple random sample of this pretty large population, we remove all these problems. Our simple random sample for a large enough sample size, maybe size 30, is going to include all sorts of students, fully online students, Pocatello main campus students, maybe some students on some of the weird campuses. I shouldn't say weird, that's rude. Some on the satellite campuses, like on the one in Twin Falls and so on. Maybe some master degree seeking students and so on. Other sampling designs will find a way to ensure that. But like we mentioned, we're going to mostly focus on the so-called simple random sample. Next thing we want to do is we should show at least once, how do you even take a simple random sample? What does that look like? If you ever have to do a big capstone project, say for a biology program or so on, you may have to do this yourself to take a random sample from a population. So we'll show it. But any questions at the moment before we take a simple random sample of all ISU students, or at least simulate what that would look like? Okay, this is part of the notes is more just for the sake of understanding the definition. It's not a project I would ask you to repeat because we're using specialized software, not that specialized, it's Excel, but you're never required to load up Excel for this class. So what we're about to do is just to illustrate that key definition. Our statistical methods are going to be fundamentally in this book all about having a simple random sample. A simple random sample of size n, this had size 6, but it wasn't random, is selected from a population in a way that every different possible sample of size n has an equal chance of being selected. So that's the heart of what a simple random sample looks like. To implement this in actual practice, here's what we could do. We would load up a statistical problem or statistical program. The Ch10 Plus, sadly, is just not big enough of an environment to do what we need to do, especially since this is a huge population. Excel also has its limitations. You probably use some specialized software. There's a whole program called R. That's its real name, just R for statistical computing, that does this stuff pretty nicely. But Excel is just a good one to show what this looks like. So first thing we need is something called a sampling frame. This is just another way to say we're listing out the population in a particular way. If ISU was doing this, they'd be listing out student numbers for every single student that's registered at ISU, and they could just spit this out of their databases. The competing universities doing this are going to have to get more clever and find a way to identify a number. We'll just use 1 through 11,000. So that number is assigned to every unique individual in this population. You can see how this is a really big problem. These kind of studies are costly. To try to investigate a population that's large, you really do have to work pretty hard, especially if you're going for the simple random sample. So our sampling frame is going to list out all ISU students. Here's student 1. This is going to take a while, so we'll use this trick. Here's student 2. And the next trick is you can just drag this down to get a whole bunch more students. Again, you don't have to repeat this for the course. This is more just to understand how to do the simple random sample. Drag it down further. And Excel has this cool feature where it just starts to go faster and faster. There's probably a better way to do this, but here's the brute force method. We're going for around 11,000. And it really got accelerating around there. So that'll do the job. I don't know the exact student body count. They'll tell us that data once they get closer to the end of the semester. Let's assume it's 11,100 exactly somehow. So we have all the students listed out in the one column. That's our population. Now we want to take a random sample. Now let's not go for 6 students. That was pretty low. I think a decent study for trying to make it cheap is going to be closer to maybe the 20 or the 30 range by this blunt rule of thumb. If they had a little bit more funding, maybe they're going for a student body, a sample size of maybe 100. Let's say we're doing 20, just so that we can see it all on one screen. We don't have too many rows. Take a simple random sample of n equals 20 students. So how are we going to do that? We need some randomization in here. And randomness is another thing that's a kind of a weird idea. The computer doesn't actually give you random numbers. This is a program that gives you a random number. Random number, let's just say that here. It goes like this, rand with a parenthesis is a random number between 0 and 1. They really look random. They're sometimes called statistically random in the sense that for the purpose of doing this in real life, selecting a random sample, they're close enough to true random numbers to be good enough. But a computer program gave us that number. If you could figure out how the program works, how it started, you would know how to get the next number. That's extremely hard to do. There's lots of mathematics that goes into this. So it's one of those things where philosophically it's not exactly random. These are actually called pseudo random numbers, which is a weird name. They behave very close to what real numbers should look like in actuality. So we take this whole thing. If I double click like that, everybody gets a random number, even all the way at the very bottom. Student 11,110 has a random number as well. Now, anything you do in Excel, like if I hit the space bar, okay, not that. If I hit the delete key, it just updates to new random numbers. If I hold it, everyone's constantly getting assigned new random numbers. If I let go just randomly, it's kind of like watching balls tumble around in a Powerball or something like that. Everyone's got a random number, and this is very close to true randomness. So what can we do next? We have to take 20 students in a way that no one gets biased, that every possible grouping of 20 had an equal chance of occurring whatsoever. These numbers would help us. Anyone see what a good suggestion would be next to get the random 20 students? I feel you. That's kind of a weird process, right? One thing that I forget is I have to do a quick fix here
I just don't get what you're doing with the other.
with this column here for the randoms. Yeah, that's going to be kind of the heart of what we have to do next. Hang on, there we go. The big takeaway is all of these are totally random. Student one getting a 0.26 had nothing to do with their position in the roster, the sampling frame. And if we hit delete again, it's just another random value. So you know what? If you sort this, it's like getting your top 20 students totally at random. You can sort both columns. Let's go to data sort, either from smallest to largest or largest to smallest. I like to go sort by the random number, definitely. I like to go highest to largest. Thinking the high number being like a high score, you made it into the sample. But if everyone's score was completely random, and it really is pseudo-random for the a bit of honesty on that, then getting a high score was also pretty random. So if I look for the 20 highest students, they fell into this completely at random. That's the way the random numbers are working on this. So all these students no longer sorted from 1 to 11,100. These students in particular had the highest numbers that came up. But once I ran the operation, the random numbers changed again. So that's why we don't see those highest numbers any longer. These are the top 20. Everyone got their number at random. It's random how you got into the top 20. Run this again, change the random numbers, sort it again from largest to smallest. And here's your next top 20. Again, the values got reassigned the moment we did any operation. So that's why we're not seeing the highest to lowest any longer. But this is the next top 20. These come in totally at random. And so this is the random sample. Kind of weird in a way, but does it make sense what the madness is behind the randomization? Okay, so if you ever have to do that, this is the idea. Other computer software just does this sort of automatically. You just say, here's your frame, give me 20 random values, and it'll just spit it out. It's basically doing something that we saw here. It's giving you everyone a random ID, the random number, and doing some sort of sort after the random number is assigned. Let's do this one more time. Do a full randomization, maybe count to 5, something along those lines, and just let go. Even if I hit delete once, that was already a random assignment. Just feels more random doing it that way, even though it really isn't. Select these. And what I'm going to do next is fix this column. Copy it in. Now I took away the fact that these are random numbers any longer. I'm going to resort the first 2 columns from largest to smallest. And here's that sort. I took out the random. I just copied in the number now. So now you actually see those top 20 random numbers that was actually assigned. Those students, student number 5,755, got his random number purely by chance. So he's in my sample of the top 20 random numbers purely by chance as well. It's in that way we've generated a simple random sample. Every sample size of size 20 has an equally likely of being in here. There are no biases whatsoever. And the bigger the sample gets, the even more representative it becomes. So here's our sample size. It would be those students in particular. Let me just copy it this way. Here is the random sample. That didn't work. Let me try again. So it'd be those students. So this is how statistics looks. Whenever you have a way to say who is in the population, you just build a sampling frame, a database of every single individual, assign them the random number, and this is what a simple random sample looks like. These students got here purely by luck. That's it. And every group of size 20 gets in there with an equally likely chance as well. So these students, if we could really simulate this, we probably would use student ID numbers. They would represent ISU very well. There's probably graduates, undergraduates. There's probably night class people, fully online people. They're probably mostly on the main campus because most students are. But there's probably some rare students that are on a satellite campus like Idaho Falls, maybe Meridian, Twin Falls, maybe just a few. But the larger the sample we make, the more we can make sure they're included. Well, let's just copy this in just as a quick reference on what we mean by a simple random sample. This is one part of the notes where the video is going to make more sense, but I feel like it's a good idea to put in something. So here's that thing for a simple random sample. If we did this process, this is now representative sample. And so the big takeaway now is because this is representative, it would be a fine estimate to say the sample mean mu would be approximately equal to, sorry, I said that backwards. Let me try again. The population's mean mu would be approximately equal to the mean of the sample y bar. So we'd have to figure out what their GPAs are once we've decided who we're contacting. Probably got to put in a humongous incentive there to actually get them to give quality information there. And this would be a good estimate. The reason the course is so long is we can't stop there. Inferential statistics is also all about doing the next step. We must also describe the error in this approximation. The moment we can do that, we can say the population's mean is approximately equal to this value with this level of confidence or with this margin of error. So we'll be able to say the full story. The one estimate here is not doing it quite enough for us. In fact, we never even mentioned the standard deviation. It's part of the story as well. But any last questions at all, folks, with this rundown of what inferential statistics looks like so far? Okay. Well, the next hardest thing about inferential statistics is Making the conclusion come out right, that's not easy. Some conclusions are too big than they should be, and sometimes you make a conclusion, but it should have been a stronger one. This all has to depend on what kind of study was it in the very, very first place. There are two major studies that we're going to be looking into, the observational studies. This one was an observational study versus an experimental design. So that's our next part of the notes. And here are those two definitions. I think these are tough definitions to be honest with you. So I want to highlight the part that kind of really directs you which one is observational, which one is an experimental design. Let's read through these carefully. An observational study is a study in which a person conducting the study observes characteristics of a sample selected from one or more existing populations. Well, that's kind of what we were doing in this problem we were looking at. We took a population, all ISU students, we observed a characteristic, what is their mean, and then we just computed an average. So that's what an observational study looks like. We didn't tell these students what classes to register in. We didn't tell them what campus to be on. We were just observing what's already happening. These students as they were in fall semester 2025. Now compare that against an experimental design. In a designed and controlled experiment, or just experiment for short, it's a study in which the person conducting the study considers how a response, say a sample mean, behaves under different experimental conditions. Could our study we just did and simulated be an experiment? Probably not. It'd be unethical. What would be the experimental conditions? You are going to be on this campus, Pocatello, Maine. You're going to take a day class. Maybe that's an experimental condition. And for the next student, we'd say, you are going to be on Idaho Falls campus. You're going to take a night class. Maybe that's the next experimental condition. No one could run that experiment. You can't tell students what classes to take. You can't impose those kind of conditions on students. And so experiments are something that are kind of restrictive. Looks like the study really couldn't really be an experimental design, but that's what an experimental design would look like. We're telling people to behave in a certain way, applying different treatments to them and seeing what happens. What is the GPA going to be if we say you're taking a night class versus a day class? Again, when we couldn't ever run that experiment. In fact, probably the best way to try to run that experiment is to get funding, but no one would fund that. There's lots of ethics when it comes to using humans as subjects. And even something like that would just be really weird. It'd probably never make it past the review board. Now, here's the major reason why we're so concerned about this dichotomy of observational versus experiment. When we do an observational study, trying to figure out what color just seems like the best one to emphasize here, our conclusion is limited. We have a limited conclusion that can never convey a statement of cause and effect. We've talked about this pretty briefly before. I think when we were looking into the contingency table in chapter 3, we mentioned no matter how interesting this data looks, we can never say one variable caused an occurrence in the other variable. It had to have been a design and control experiment to make that happen. Let's take a look into that just for the sake of tying this together. This was all the way back in chapter 3, relationships between two categorical variables. This was the two-way table. And we're looking into the relationships between hepatitis and tattoos and where we got them. And some of our percentages and some of our bar charts painted a pretty vivid picture of a relationship. But at no point could we ever say for this problem that getting a tattoo caused a higher occurrence of hepatitis C. That's absolutely off the table on this. This could never be an experiment. You can't tell people you're going to get the treatment of getting a tattoo at a parlor. You're going to get a treatment of getting a tattoo elsewhere. And you have the treatment of you're not going to get a tattoo. We let some time go by and see who gets hepatitis C. There's just no way this ever could be ran. If you try to run this kind of experiment, you're probably going to be blacklisted. People are going to think that you're some kind of crank or something like that. It'd be just tremendously unethical. This was just an observational study. At best, we could talk about how the variables relate, but at no point could a conclusion of cause and effect ever enter the picture on this one. So that's what was going on that one. I'm not too sure if we've looked into a direct experiment when we analyze data. We will later on in this course. The experimental design is special. In experimental design, the person conducting the study considers how the response behaves under different experimental conditions. Maybe we're studying like a sleep medication. We're going to measure how many hours of sleep you've gotten. We're going to take the medication and we're going to get a placebo effect or a placebo tablet as well, which is some benign ingredient, maybe a sugar tablet. Two of the drugs are going to look similar, and people are going to be randomly assigned to get the active ingredient versus the inactive drug, the placebo, and we'll just compare the response, how much sleep you've got. If one group slept more, hopefully the one that had the active ingredient will say the sleeping medication caused the additional sleep. Only if the experiment ran correctly. So this is the good news about experimental design. Here, we can make conclusions for cause and effect. If there's an effect after we've done the experiment, sometimes there's no effect. Sometimes the drug isn't more effective than the placebo. But if it is, we'll say that the treatment, having the drug, caused that improvement or whatever condition that we happen to be studying. So that's the big dichotomy so far. But again, this affects the conclusions that we write when we're later on and say further into chapter 13, chapter 14, and 15. Knowing what kind of study we're dealing with tells us what the conclusion actually looks like in the first place. Further information is the goal from the observational study is to use the sample to learn about the corresponding population. And in an observational study, we need a representative sample, say a simple random sample. Compare that against this. In an experiment, it's important to have comparable experimental groups. So if we're testing a drug, we want people to be all of the same sex, potentially all male, all female. We want them to all be roughly the same age. If we need to test other age groups, we need to run a different experiment or start blocking out the experimental design for different age groups. We're looking for people in the experiment or whatever the individuals happen to be as similar as possible. So the thing that changed was the experimental condition, say receiving their drug or not. That way we can say the change we see in the data was caused by the different treatments, not by the individuals themselves being different. It's in stark contrast to what's going on here. But you know, both has randomization. Here we select a simple random sample or some other clever sampling design. Here, the person carrying out the study determines who will be in each experimental group and what the experimental conditions will be. And you know, there's one word I was hoping there, should be there. It looks like not in this book's definition. The person carrying out the study determines who will be in each experimental group. Let's add this additional word, using randomization. So the subjects in the groups don't get to choose which treatment they're going to get. You don't get to say, I would like the active ingredient drug versus the inactive placebo. This is all by randomization. And that's how the randomization occurs for the experimental design. It's at random what treatment you get, and you probably wouldn't know as a human subject what treatment you really are getting in the first place until the whole study has been concluded. So the major takeaways in an observational study, we're just observing what happens and making some conclusion based on the data. In an experimental design, someone is choosing what treatment that you're getting, what experimental group you're belonging to, And they should be using randomization as well. We just baked that into the notes just for extra emphasis. Now, determining which is hard, especially when we're doing it in a real problem like this one. This is an actual study published a while ago, about 10 years. We want to decide, is it an observational one or is it an experiment? First, any questions about these two definitions so far? Okay, they are tough definitions, so let's think about them as we read through the context. That's an interesting name, baby scientists experiment with everything. It was a study published in the Journal of Science, and Wall Street just reported on it. So that means that's a pretty big journal. And it says in one of these studies, 11-month-old children were assigned one of two groups. That's interesting already. If you're being assigned groups, that sounds like one of these two already. So let's think about what it could be. The children in one group were shown a ball behaving as expected, such as rolling into a wall, falling off a ledge, just ordinary physics, and the baby was probably kind of disinterested. The children in the other group, these are 11-month-old babies, were shown a ball behaving in an unexpected way, such as rolling through what appeared to be a solid wall, rolling off a ledge, remaining suspended in air. So they had maybe a magician running this and just showing a baby physics breaking, basically. So that's what they did with these 11-month children. They were each in one group or the other. Then the children were given a ball and another toy. Researchers found that the children in the group that saw the ball behaving as expected didn't care about the ball. They showed no preference. They probably went for the ball or the toy about 50% of the time, close to half. But the children who were pranked, basically, the one where the magician showed the ball doing weird things that disobeys physics, the children who saw the ball behaving in an unexpected way tended to choose the ball. They're interested in that thing now. And they also played with it differently and tested the ball's behavior before by dropping it or rolling it, probably just to see if they could recreate the illusion that they saw. That's kind of interesting already from a psychology standpoint that at 11 months old, they're trying to deconstruct what's going on around you. The question now is, what was this? Is this an observational study or is this an experimental design? And why? Let's go for the bigger question. Anyone see which one it should be? Just put the red dot in a neutral spot. I agree. This was an absolute bona fide experimental design. So let's say here, this is an experiment. We have to explain our answer. So what would you say is the big giveaway that makes it an experiment?
Different things they show.
Yeah, that's really two experimental conditions, really. So the children in one group showed an ordinary ball. The children in the other group were shown a ball behaving in an unusual way. This right here is what's being referred to when it says, the person conducting the study in an experiment considers how a response, the response is how the child played with the ball versus the other toy, considers how the response behaved under different experimental conditions. These are the two different experimental conditions. There has to be at least two. Sometimes there's a lot, depending on how convoluted the study is. That alone made this an experiment. And that means their conclusion is really profound. They can say showing a ball behaving in an unexpected way caused these children to prefer the ball and to experiment with it. There's real cause and effect that they got out of this study. So let's put all those thoughts together. This is an experiment. I guess that should be like a common how, because there were two experimental conditions. That's how our author wrote this out. Those experimental conditions were the ordinary ball And the other condition was the unusual ball, the one that seemed to float or go through a wall. Really, that's the whole problem. Decide if this was an experiment or an observational study and explain why. Let's add just the additional thing. The reason why we care about this is the conclusion they make is big. The experimenters can conclude, sorry, say again, experimenters. I think so. There's experimenter, and so this is just the plural of that, but looks funky on paper, honestly. The experimenters can conclude that the ball behaving in an unusual way caused the increased interest. So the moment we know that this was an experimental design, we have cause and effect in this problem, and that's something that they would have written out in their conclusion. If it was an observational study, this whole part, even if we hinted at it, would have been really bad form. The journal Science, if they knew it wasn't an actual experiment, they would have never even published it. If they did publish it, the next journals would have probably redacted it and said, we made an error. This study didn't belong to the journal. Here's what the problems were with it. It wasn't an actual experiment. If certain elements of the experimental design didn't work as expected, they might not have published it as well. So the fact that they did publish tells us they ran a great experiment, and this was an interesting conclusion. So that's what an experimental design will look like. Any last questions before we try out the next one? Okay, by elimination, we're all expecting the next one to be an observational study. But let's see if we can detect why, what makes it observational. So this one's a hard one to think about because experiment clearly says there are different experimental conditions, and that's the thing that we look for. But that's a great hint. You can say something is an observational study because there was no different experimental conditions. That's what makes it observational. Let's throw that into here just as another way to think about an observational study. A study is observational if, let's actually make this a broken down statement. There are not multiple experimental conditions. I know there's a little more to that. Or a big part of what makes an experiment is someone conducting the study chooses who is going to go into each one of those experimental conditions. So that's just as important as well. So we might look into some problems where there's multiple different I shouldn't say treatments, but multiple different conditions. But if no one said that these people go to this condition, by randomly, the other part of the study goes into a different condition. If it's not controlled in that way, it still isn't an experiment. So this is equally important. Let's say, or there is no experimenter assigning the subjects to the different experimental groups. So if we just look at data as it was, we didn't assign people to those groups, it's observational. Or if there is just not multiple different conditions we're looking into, it's also not an experimental design. We're just looking into an observational study. And that takes us down to example 2. It says the article, How Dangerous is a Day in the Hospital? This is medical care from 2011, so even older data, describes a study to determine if the risk of an infection is related to the length of a hospital stay. Notice that word related. It's a pretty targeted word. Next, it says the researchers looked at many hospital patients, compared the proportions who did get an infection for two groups of patients. There is multiple groups on this one. Those who were hospitalized overnight and those who were hospitalized for more than one night. So that's 2 conditions. Hospitalized one night or multiple nights. The response is, did they get an infection or not? But this one doesn't pass the test. It's not an experiment. It has the multiple conditions, one night versus multiple nights. But you know what you can't do with human subjects in a hospital setting is you can't say by random assignment, you're going to stay overnight. I don't care what your condition is. And you other people are going to stay for multiple nights. That can never happen. The doctor makes that assessment, not the experimenter. You can never run an experimental design in this kind of case. We just looked at the patients as they were. They fell into those groups just in a natural way. There's no randomization at all. That's what makes this one observational. There's no experimenter assigning people to staying one night versus multiple nights. Let's put that in words. There was no experimenter assigning subjects to the conditions of one night versus more than one night. So that alone says this is not an experiment. And that's why they use the word related here. What they absolutely could not say, if they said this, then they're going to be in really big trouble. The journal, if they publish this conclusion, is going to be under fire as well. It's going to be thought of as not a serious journal any longer. They cannot say the following. The study can not conclude that the length of stay causes a higher likelihood of infection. There's no actual cause and effect in the study. And it seems frustrating because we might want to bring in our own subjective intuition into this. We might want to say, just from what we expect, we think staying in the hospital longer could cause me to be more likely to get an infection. But that's not the conclusion at all that this study could ever give. That's why they said related. Anything that hinted at cause and effect would have been really bad in this journal. They just said, well, there is a relationship between lengthened stay and the incidence of infection. They might say something along the lines of, it seems that there, for a higher length of stay is related to having a higher infection rate, but they can never say longer stays in hospitals cause higher chances of getting that infection. These are just 2 things that went together. So cause and effect are really tricky things when you think about them. For example, for kind of a really absurd example, think of a situation as really big fires and the response of firefighters. Everyone knows that a fire can cause the firefighters to come to the scene. But if we get the cause and effect mixed up, we might just get that backwards and say firefighters cause really large fires. But that's absurd, right? We have to think very carefully about cause and effect, the direction things can go. And without a bona fide experiment, did we ever address that? There was no experimenter assigning subjects to the conditions of overnight or more. If it was just an observational study, sorry, I should have completed that thought. This is an observational study. With just the observational study, that's all we can get, that there's a relationship between the two conditions. And here's another extreme example. Cause and effect is really very, very tricky. And back in the day, if you go back decades, the open question was, does smoking cause cancer? And everyone who was working for the smoking industry said correctly, if you don't run the experimental design, there's just a relationship. Higher smoking is related to higher incidence of cancer. But in court, and they won, they said there's no cause and effect here. This is just a relationship. And you can't run that study. You can't put human subjects to chain smoke and other human subjects to not smoke and see who gets cancer, who doesn't. They eventually did get to cause and effect. They found the actual mechanism in the cell that goes wrong, that gets gummed up by the actual tar, nicotine, and cigarettes. They showed biologically how cause and effect actually happens, but they couldn't do it statistically, not without an enormous amount of work, not from one observational study, certainly. This was a huge mountain of evidence that they had to pour onto that kind of problem. But that's the short of observational versus experiment. Experiments are extremely powerful. And observational studies, even if we want to say cause and effect, it might be a little bit of evidence in that direction, but it's just like a drop in a bucket. We're limited to this really restrictive kind of conclusion. But any last questions or comments about those kinds of studies so far? Okay, these are tricky definitions, so that's why it's worth spending time on them. It affects the rest of the course because we'll occasionally say something causes something else where we know we have an experimental design. The next elements of the notes is getting back into the differences between parameter versus statistic. These are tricky too. When we've been talking about them for a while, this came up in, say, chapter 6, when we're looking into, not chapter 6, excuse me. These things came up in chapter 5, when we were modeling a population using the normal distribution. Let's take a look into the way that came into to the course. Parameters became a thing for us in just this problem right here. These are parameters. We have a population of the snowfall that could happen in Rochester, New York, in the month of December, year after year. And we decide to model that population with the parameter mu, the mean population mean, and a parameter sigma, the population standard deviation. But what was tricky about that is we weren't actually saying we know mu is 21.9. This is just a guess, similar with sigma. It's much like what we were pointing at before. Once we collect random data, we make an estimate like this, that's also just a guess. We don't know mu, not exactly, unless we do one thing specifically, which is almost impossible in a lot of applied situations. The only way you'll know the exact value of a parameter is if you take a census. A census involves the entire population. So if you have the entire population that you can access, you can calculate a parameter. A parameter describes the entire population, and the parameters we've seen have been so far mu and sigma. We'll take a look into others. The statistic describes a sample, and statistics that we've seen so far have been y bar and s. But not once, not in one single problem, have we ever had a census. Even the US government tries to do a census. They're required to by the federal government, but it's questionable how accurate that census is even for them. When they go to take their census, they're still approximating the parameters because there's questions about accuracy in just that USA government census. That makes example 3 pretty exceptional. First of all, this is a shout out to something I mentioned before. I don't necessarily hate USA Today, but it's kind of like what's the word for that? It's one of those magazines where all the articles feel like they're clickbait type articles. And that looks like a real clickbait kind of title. The title was Soldiers Hate Their Jobs. That just seems inflammatory. They're just trying to make you buy the magazine. For it was a website, just trying to get you to click on it. And this was what was reported. It was reported that 52% of soldiers surveyed were pessimistic about their future in the military. And that's true. This statement is based off real data. It's based off data collected in the 2014 annual assessment that all soldiers must take every year. So USA Today had a really crappy title. It's inflammatory, just designed to piss people off, I think. But their data is real. 52% of the soldiers were pessimistic about their future in the military. But you have to define pessimistic as well, and that's barely over half, 52%. So that 52% is interesting. It says if the population of interest is all soldiers serving in 2014, does the group of soldiers surveyed represent a census or was it a sample? What would y'all say for this one? Do we have a census or just a sample in this particular problem? It turns out that this one is, by a weird part of the problem, it's really a census and it's kind of hard to see. Almost like 99.9% of the time, you would be right. Our studies are just giving us samples, but there are some really rare exceptions. This one turns out to be a census, but can anyone see why, in this context, it was a very effective census, probably more accurate than the US government census? Exactly. It's an annual assessment that all soldiers must take each year. It's an order. They have to do this. I don't know exactly how the military works. If they didn't do it, who knows what would have happened to them? Probably not discharged, but probably reprimanded or something like that. But I would believe that the success rate of getting the population, all soldiers in the 2004 enlisted in 2014 or serving in 2014, I bet you they had a really, really high success rate. Just about everyone did this at some point or another. They did this assessment. So this data is based off a census, and this is one of those rare situations. Since all soldiers serving in 2014 were absolutely required, I'll just say required, to take the assessment. This is not the full story, but also the population of interest is those soldiers serving in 2014. And since all soldiers serving in 2014 is the population, this was a census. It deserves an exclamation mark because once you have a census, you know mu and sigma. Well, this one's a little bit different. It's a percentage. It's not exactly like mu and sigma. It's going to be something new. P. We'll call that a population proportion. But that's the parameter we're looking to. The reported percentage, 52%, because we're dealing with the census, and because the census is an entire population, 52% is discussing the underlying population itself. All soldiers serving in 2014 is the population. So we can say here, P equals 52% is a parameter. And no further statistics has to be done. There's no error in here whatsoever. Now, this is assuming 100% of the soldiers took this assessment. Even though that might not be dead on accurate, it's probably extremely close in this one situation. Here, the statistics just ends at this step. There's no further work. There's no chapter 13 on confidence intervals, chapter 14, 15 on hypothesis testing. The course is just over if all we deal with is census. We just stop at that point. And it gets interesting for us because we don't often have a census. This is really rare. If we didn't have the population proportion P, the 52%, if this was just an ordinary sample, we would have had something else. The statistic would have been called P hat. This is the sample proportion. And just like we've been hinting at the notes all along, including day one, first week of the course, it is true that P is approximately equal to P hat, but this isn't good enough for us. The course just goes on to week 15 because our task now is to say, what is the reliability of that estimate? What is the margin of error? What kind of confidence interval can we give for plausible values of the unknown P? But in this one rare example, example 3, life is simple, the whole statistical job ends right there, the moment they calculate that percentage. By the way, just like there's synonyms, mean can be thought of as an average, that's a direct synonym. Proportion is synonymous with percent. It's just a unit change. As a percentage, it says 52%. As a proportion, P equals 0.52. We just move the decimal place 2 positions to the left. So we'll look into a couple more problems along these lines, spotting the difference between the parameter and the statistic. And in chapter 13, we're going to start studying P and P hat in full. The thing that's really crazy about this and kind of miraculous in a way is the normal distribution just comes right back. We'll simulate that to see it visually, how that's all working. But any last questions at all, folks? Finalizing that example 3. Okay, so this work here, the parameter versus the statistic, this is the stuff that's going to be the nuts and bolts of the work we're doing in chapters 13, 14, and 15. Everything up here, this is just the nuts and bolts of what does our conclusion look like? Can we say cause and effect? Or do we just say there's a relationship between what we're seeing in the data? So we'll finish off these notes when we come back next class and dive into chapter 13. Another call out to chapter 13, it's probably one of the more abstract chapters of the entire book, chapter 13 in its entirety. It's a good one to just skim, even if you look at it just for a few moments before we come to class, and it helps out a lot. If you're seeing this stuff for the first time, we'll go slowly and carefully, but it is a little bit extra hard. If you've already previewed it a little bit, any preview you do makes a lot more sense when we go through the notes over here. But aside from that, have a great weekend, folks. We got through a lot. We're way past midterms now. We'll be just right back here on Monday next week. Any questions?
Yes. So the exam that I missed,
Yeah.
So do I just, how do I make an appointment to do it at the